Okay, let's begin. So, Kyra was already way back there, and I was like, to move the camera back, I might as well just move it a little back and get the whole board all at once. So, you guys can watch this video and see if you prefer this perspective as opposed to the move to that board, move to that board, move to that board. Couple things before we begin. One important thing, next Friday, I think, is the last day to drop the class. Okay, so, not insinuating anything, but I want to tell you what your options are. It's only fair, right? So the thing is, I wouldn't finish the topics for chapter 6 today. I'll definitely finish by Thursday. The problem is, if I finish Thursday and I give you guys a whole week, I'll have to give the test next Thursday. There's no way I'll have them graded by Friday, and you'll know what's going on. So the other option, which I can put to a vote, is we can choose to finish on Thursday and I still give you the test on Tuesday. Which is an option. Personally, I think we can go for it. I don't think the last two sections that we're going to do are difficult compared to the ones we've already done in chapter 6. But it's up to you guys. If you think you can actually manage the test on Tuesday, I could get it graded to you and give you back on Thursday, and then by Friday you'll know what to do. But otherwise, if you insist on having the 2 extra days, then would you guys rather just keep the test on Thursday as opposed to Tuesday? Okay. Well, if you guys know you're sticking around no matter what, then it won't matter. But if you're sort of considering dropping the course, probably knowing how you do sooner rather than later would be a good idea. I guess. So I guess we can keep the test for next Thursday, and I guess the couple individuals who might be considered dropping, they can see me on Thursday and be like, I need you to grade my test like right now. and then we figure, because I don't know how it is. Okay, so then we'll just play it by ear. So today we're going to, I pretty much want to finish section 6.5 and move on. I'll start 6.6, I won't finish it, but I'll try to start it at least so you can start working on that. Anything else I want to announce? Yes, I sent out the reports. I don't know if you guys saw them, but they should be in your emails already. So I sent out the report card so you know how you're currently doing in the class. If you emailed me at the first day of class, I would have your email to send out the reports to. So you can check that just to see your overall, how you're doing overall. The attendance is not updated, but pretty much everything else is, so it gives you a good idea of how you're doing. So I sent those out like half an hour ago or 40 minutes ago, so you should just, so you can check those afterwards. Something else to say, one other thing I want to mention. Yeah, my other class, they did slightly worse than you on the first test on average. So I felt, Calc 3 is my other class, I teach Calc 3 as well. I felt compelled to give them like study tips or whatever. So I actually did that during the lecture when I know everyone would be there and paying attention. So I can probably just email you guys a link to that class. I can see like, oh, watch the first 10 minutes of this video and you'll see study tips. Because I realize a lot of them were sort of studying in the wrong way. So I want to make sure that none of you are actually doing that and you're studying in the most optimal way possible. For example, if you study from your homework and notes, that's the wrong way to study. Right? A lot of students seem to tell them, oh, I studied by practicing the homework. That's not how you want to do it. So I specifically talk about how you should study for this course, and I can send you guys a link to that. I think it might help some of you here. Yeah, that's it. For now, we're going to move on to approximate integration, which you're going to need your handouts. We're going to be using these guys that I gave you last time. As you can see, there are a lot of formulas to this section. No way around it. You're going to have to memorize them and use them. Because I can't give you a formula sheet. So we're going to talk about that now. Approximate integration is section 6.5. By this we're just taking a computational approach. Two definite integrals. Right, so it's sort of like we're going back to that whole Riemann sums approach to computing integrals, but we're going to actually look at other ways of cutting up our integrals, and we're going to be using that. It's computationally intensive. The good news, though, is it's plug and chug, really. It's not going to be conceptually difficult to get. Once you memorize the formula, you're just going to be plugging numbers into a formula. Right? So I'm going to tell you, use this kind of approximation and use this number of dissections, and then you plug in the formulas with those numbers. So it's very plug and chug. Gonna rush through this, not really gonna derive or anything. I'm basically gonna tell you the formulas and have you apply them. I don't particularly see any reason to go deeper into this. It's not really something that's gonna be terribly consequential to you in the future. So, the idea, why it's important. I don't want to spend a lot of time on this because even mathematicians wouldn't actually do this by hand. Like, we'd use a computer, right? If it's just a plug and chug formula, you can just program it, right? There's really no creativity involved here. It's just a formula, right? So we wouldn't do this by hand. So I'm not really going to spend too much time on it, but I'm just going to show you. But why it's important is a good thing to know. So for example, notice that this guy here, e to the x squared, has no antiderivative. Right? For example, right? We cannot integrate e raised to the x squared power. It doesn't have an antiderivative. There's no function that we can think of where when you differentiate it, you get that as the answer. Right? So it just doesn't work. It's not something that you'll be able to do by hand. However, we can approximate a definite integral of this kind. A up to b of e to the x squared, we can approximate that, right? To any degree of accuracy we want, in fact. To any degree of accuracy we want. And how we do that is approximate integration, or it's sometimes called numerical integration, right? It's basically plugging and chugging a formula. So the idea is, this guy is doing something, so it's going to sort of look like a parabola, but it's increasing exponentially. And so basically if I want to say, find what's the area under the curve between 1 and 5, I'm going to do approximate integration. I'm going to cut this up into rectangles, and the more rectangles I use, the closer to the answer I'll be, right? So I can't find the exact answer because the antiderivative doesn't actually exist, but I can use enough rectangles to get as close to the answer as I want, right? So that's basically the idea of why this is important. Okay? So that's sort of the reason why we need this, right? So now you sort of know the reason. That sometimes we can't integrate things by hand, and so indefinite integrals are impossible. But if we're given a definite integral, which would actually show up in reality, that's actually a very popular function. It shows up all the time in like probability and statistics and all that stuff. It actually shows up in real life. But yeah, if we have limits on this thing like 0 to 1, I could actually approximate that value, and that's how we're going to be using these guys. There are several rules we're going to want to go through. The approximation rules we will use. The first two you guys will know already. There's like a right-hand rule, it's called. There's the left-hand rule. These are some of the most popular ones, the ones we'll be doing in this course. I'm actually going to illustrate them and then give you the formulas. There's what's called the midpoint rule. There is going to be the trapezoid rule. And finally, I think the last one we do is Simpson's rule. Is that all we're going to do? Yeah, midpoint, trapezoid, Simpsons. So let me just show you the difference between each. So the idea behind the right-hand rule. Let's say I'm given a function that I want to approximate the definite integral, say between a and b. Right? The idea is we're going to cut this guy up into n rectangles where I'll tell you what the n is. I'll say use 4 rectangles, use 5 rectangles. Or I might say use 4 subintervals, right? So that's the sort of language, right? And how we actually set this up is the right-hand rule says the height of the rectangles will be given by the right side of the interval, right? So I'm going to break these guys up into several subintervals, and the right side of each interval, right? So here's the subinterval. I'm going to look at the right side, and that is how I'm going to define the height of this triangle, this rectangle. So it will look like that. Then I look at this subinterval, the right side defines the height, right? This subinterval, the right side defines the height. And this subinterval, the right side defines the height. And here, the right side defines the height. And then, by adding up the areas of these rectangles, I can approximate the area under the curve, right? This is using the right side. Left-hand rule is just a Riemann sum. We'll get into the specifics here. Left-hand rule is pretty much the same idea, except now I'm going to be using the left side of the intervals. Right? So I'm going to cut this up into certain intervals, and on each subinterval, I'm going to use the left side to get the height. The left side gives me the height. I'm going to use the left side, giving me the height. Again, the left side gives me the height. Left side gives me the height. You'll immediately start noticing some differences here. Notice on the right-hand rule for this particular kind of function, I'm getting an underestimate. Like a lot of the time my rectangle's area is smaller than the area under the curve. Well, notice in the left-hand rule, my rectangles tend to be above the curve, right? So this approximation will give me something slightly larger than the actual answer, while this will give me something probably smaller than the actual answer, right? So there are different approximations, and they might work out differently. One might be a better approximation to use than another, right? So let's say I have the same function. Now I have A, B, right? The midpoint rule, again, we use rectangles, so we're going to cut these guys up. But now the thing is, we're going to use the midpoint of each subinterval as the height, right? So between each subinterval, I find the middle number, and that's going to tell me the height of my rectangle. And so what you see here is it gives you a slight overestimate, but then it takes a slight underestimate. So there are cases when we might think, oh, this is a better approximation because it's give and take, right? So you do the middle, that defines the height. Do the middle of this guy, that tells you the height. The middle of this guy, that tells you the height. The middle of this guy, that tells you the height. So it's like we're taking Riemann sums, we're going to be using rectangles, and area is going to be length by width, just as before. Trapezoid rule. So in the trapezoid rule, the idea is we don't want to use rectangles anymore, we use trapezoids, basically, right? So this allows us to sort of more model the function. Right? So if I'm here, I'll cut this up into several intervals. I'm going to use a trapezoid. So notice here, I notice the function is sort of increasing. So I've cut the rectangle like this, right? So I'll take the two endpoints here and create a trapezoid, right? And then I'm going to find the area of that trapezoid to approximate the curve. Or this, it won't be an exact rectangle, it's going to be a trapezoid. And then I'll connect that. Then I'll connect that. Connect that. So you see, I'm not using rectangles anymore. I'm sort of using trapezoids so that I follow the curve closer, right? And that's sort of supposed to give me a better approximation much quicker. In Simpson's rule, we get really serious, right? And we go crazy. We're not even using polygons anymore. Now we're using curves. In Simpson's rule, we actually approximate using parabolas, right? So I hit here, and I'm going to find a quadratic function that sort of cuts here. And I'm going to do this, and then find a quadratic function that sort of stays close to this. This, find a quadratic that stays that. This, find a quadratic. This, find a quadratic that goes this way. Right? So that's sort of the main difference between the two. Something that's common to every method that we're going to be using is the width of these rectangles we will call delta x. Right? That's just the change in the x value. We're going to do it in such a way that we're cutting these up into equal subintervals. So all these lengths here will be delta x. Right. I'm going to tell you what formula we can find delta x with. Right? But yeah, all these width of these rectangles, we call them delta x. Right? The height of our rectangles will be given by what? The function, right? So if this function is f of x, then the height here is just going to be f of a, for example. Right? So if I want to find the area of this rectangle, it's just going to be delta x times f of a. Right? So at each point, I'm just going to figure out what my delta x is, figure out what the value of my function is at the point I want to take the approximation at, multiply those two, and add those together for all of them. Right? That's the basic overview of these ideas, and this is the difference between the different rules. So conceptually, that's what's going on. And right now, I'm going to give you the formulas for each of these guys. These three are very similar. Sort of the same rule applies. So let's do all those three at once. Because it's just area of rectangles. They're all rectangles here. That's what they all have in common. So suppose we wish to approximate a definite integral from a to b of f of x dx using n rectangles or n subintervals. Equal width. Then, let's say we're doing the right hand rule. Let me do the delta x first because that's going to be common to everyone. Then delta x is equal to the width of the intervals. Which will be equal to what? B minus a over n, right? So that comes from the fact that here I have this interval a, b. I'm cutting it up into n sections, right? These are n sections. And they're equal width. So I just take the length of this, which is just the right endpoint minus the left endpoint, right? That still gives me the length here. And then I divide it into n sections, right? So this formula is always going to be your delta x. That's an important formula to remember. Right? You have to memorize this. This is something that something that we know now. You just know this. Okay? So first of all, that's going to be your delta x. In all the rules, that's what we're using for delta x. You take the right endpoint minus the left endpoint, divided by the number of rectangles I'll tell you. So n, I'll actually tell you what it is. Right? So that's the first thing. So now let's look at the right-hand rule. you realize at the end of the day, you don't actually have to actually do any integration here. It's just plug in and chug in. So right-hand rule. So let's say here is your interval. This is A, this is B. Let's say I call this x0, and I'm cutting it up. So the next point will be x1, x2, dot, 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 all the way up to xn. So that's how I'm putting out my interval. These x values we'll be able to find. We're going to do it later. Then integral from a to b of f of x dx is approximately equal to, the notation you might see is Rn, right? This means use the right-hand rule with n subintervals, which is going to be equal to delta x, which is the width of each rectangle, times the function evaluated at certain points. It's basically what it's going to be. Now, what do you think these points are going to be? What's the one that goes in here? X. X1, right? Notice that here, on the right side of the interval, is x1, which means x0 gets ignored because it's on the left side. So x1 is going to be my first guy. Then here I'm going to put in x2. Then all the way down at the end, I'm going to put in xn. Right? So notice for the right-hand rule, you skip the first interval and you put in all the others and evaluate it. Right? That's going to be your number. Left-hand rule, again very similar. Delta x is just b minus a over n, but the integral from a to b of f of x dx will be approximately equal to ln, which we can think of as delta x times, again it's just the sum of the heights, right? But what are the values that we plug in here? Well, I care about the left intervals, right? So I'm going to start at x0, x1, and I'm going all the way up to just before the last point, right? xn minus 1, right? So the important thing is in the right-hand rule, ignore the first part. In the left-hand rule, ignore the last part. But you're just plugging into the function, right? And you're adding these all up and multiplying by a delta x. Because when you distribute, what you're actually doing is length times width and adding them all up. Similar thing happens here. Midpoint rule. So again, I'm thinking of dissecting it this way. Let me actually redraw this because the midpoint rule changes things a little bit. So here I'm going to cut it up here. So let's call this x0, this is x1, this is x2, x3, all the way to xn. Now remember what the midpoint rule does. It finds the point in the middle, right? Your textbook, I think, calls this x star, right? 1. And then the point in the middle here would be x star 2, and so on and so forth, right? Now, how do you find x1?
The next one has the right one and do it like this.
Right, it's just the average, right? So your x1 star would just be x0 plus x1 over 2, right? And you can average all the rest, but I find that it's easier for the other guys to be, you just take the previous one and add the delta x to it, right? So once I figure this guy out, I just add delta x to get to that guy and keep adding delta x to get to the other ones, right? I don't need to do an average every time. That'll take longer than we need, right? Because the spacing between the midpoints will be exactly the same as the spacing between the previous intervals, right? Because we're only shifting everything in the middle. So to get to the rest of them, you just do that. And so, integral from a to b of f of x dx can be approximately equal to mn, which is the midpoint rule, which is going to just be delta x times now f of x1 star plus all the way up to f xn star, right? Where these are just the middle values. So we sort of get the idea. We'll do some examples, but is the idea... Okay. I'll give you the other formulas, and then we'll just run through the examples that's on the sheet. Next one we're going to look at is the trapezoid rule. Not going to show you the derivation. It's basically derived from the formulas for the area of a trapezoid. So here's basically how it's going to look. You're going to cut this thing up the same way we did before. And the trapezoid rule looks like this. So here, instead you have that delta x over 2, because when you apply the area of a trapezoid, there's going to be a 2 that you can factor out. A half that you can factor out. Now there's a pattern here, and there's going to be a pattern for the next one. The first point stays the same. All the middle points, though, you're going to multiply by 2. So however you can remember that, just figure out a way to remember it. It looks almost like the rectangles, except use the first point. This is going to be your A value. This point here is going to be your B value. Those guys, you just evaluate the function there. Everyone in the middle, though, you have to multiply by a 2. So we're going to use that. And you take delta x over 2 on the outside. That's going to be your Tn, the trapezoid rule approximation. Simpson's rule formula, and then we start to actually do some examples. Here's the formula. A goes to B, f of x dx. You can approximate it using the Simpson's rule formula, which is going to be delta x over 3, and this one has also a weird pattern. F of x0, first one stays the same, but the inner ones alternate. It starts with a 4 times f of x, then a 2 times this one, then a 4 times that one, then a 2 times this one. Right? And this pattern alternates until you end up with, there's going to be 2 times the last guy, plus the function evaluated at the last guy. Here, n must be even. So you're going to, sorry, we end with the 4, because it's even. That's basically it. So for Simpson's rule, you divide delta x by 3. You start the first and last guy, you just evaluate into the function. The guys in the middle, you multiply a 4, then a 2, then a 4, then a 2, then a 4, then a 2. You continue this until you end with a 4 just before the last guy. And this, you'll always start and end with a 4 because your n must be even for this rule to even work in the first place. All these formulas, by the way, they're on the handout. So you can write them down if you want, but I already have them here. You can just measure them. Okay. Now let's talk about errors. So it's not just good enough to approximate, we also want to know how good our approximation is, right? How far are we from the actual answer? Well, that's what the associated errors are, which is what I also gave you here. So by error, I mean how far are we from the actual answer? Right? So if you could find the exact area, how far away from our approximations would it be? It turns out it depends on the size of n. So let's look at the midpoint error, midpoint rule error. Which I'm going to call EM. Right, this is the size of the error, meaning this is how far from the answer plus or minus will actually be. It's actually less than or equal to k times b minus a cubed over 24n squared, where our k is a constant with the size of the second derivative, and this is what makes it annoying because we'll have to find the second derivative of the function is less than or equal to k, which is there's a typo here. That LE means less than or equal to k on page 080. It takes forever to write out. Imagine if we were actually deriving these things. So here's the trapezoid rule error. The notation for that is ET. The size of the error will actually be bounded by k times b minus a cubed over 12n squared. K is the same as here. Simpson's rule error. ES. The size of the error for the Simpson's rule. The Simpson's rule, the k is different. Such that turns out the fourth derivative is what we have to find for the Simpson rule, is less than or equal to k. Those are all the rules. Unfortunately, we have to memorize them all. I don't know. This is a night class. Maybe I might give you the forms, but don't count on it. 'Cause, like on the actual final, they wouldn't give you the final. It's sort of being unfair for me to do it. Yeah. But can't really get around this in Calc 2. I don't particularly think it's super important. This is one of the things where I'm saying it's okay that if after you finish Calc 2 you can forget all this. It won't really matter. In the case you'll ever actually need this, just look it up or plug it into a computer and let the computer do the grunt work, right? The problems you need humans to solve are not these. So. Okay, so now we know the rules. Let's just do the plug and chug and just sort of figure out how we would do them. Because they do come on every single final, so it's something you would have to know. So let's do some examples. Right, the examples are on the next sheet. So here I said approximate this integral using 4 subintervals with the midpoint rule, the trapezoid rule, and Simpson's rule. So here's an integral 0 to pi of sine x. Right? This one we could actually find the actual answer, so we can actually see how close we get with 4 subintervals. N equals 4. A, I'd like you to use the midpoint, then trapezoid rule. B. And finally C, use Simpsons. All right, N equals 4, so N is even, so Simpsons does work. Let's just see how this looks. Let's look at the midpoint. M4 is what we're going to want to find here. So the question would look just like this. Approximate blah with 4 subintervals using the midpoint. I don't think they'll ask you for all 3, but they might ask you for a couple in a different part of the problem. Or they might ask you for just one. Right? They might approximate this integral using the midpoint rule with 4 subintervals. That could be a question. Right? So first thing you're going to want to do is you're going to want to figure out what is your AB. 0 to pi, right? The A is on the bottom, the B is on the top in our formulas. So this is 0 to pi, right? Which means there are a couple things that we can already tell. We can tell what our delta x is. What's the delta x? Right, pi minus 0 over 4, right? It's b minus a over n. So it means pi over 4 is going to be the subintervals. Which means I have the interval between 0 and pi. I'm going to cut that into 4 equal sections. The length of each section should be pi over 4. So here, I'm going to hit pi over 4. Then the next one will be another pi over 4, right? So this is 2 pi over 4, which is pi over 2, 3 pi over 4, then 4 pi over 4, right? Each length here is pi over 4. Each length is a delta x apart. Right? So now I know all the numbers that I'm going to be plugging into my function, right? If I was doing the right-hand rule, I'd plug in pi over 4, 2 pi over 4, 3 pi over 4, and pi. If I was doing the left-hand rule, I'd plug in 0 pi over 4, 2 pi over 4, 3 pi over 4, and ignore that. But here they want us to use the midpoint rule. Right? So the first thing I'm going to do is I'm going to need to find out the middle value here. Right? What's that value going to be? This plus that divided by 2. Right? So this is going to be halfway, pi over 8. Right? Now to get the middle value here, what am I going to do? I'm just going to add the delta x to pi over 8. Right? So I'm going to add pi over 4 to pi over 8, in which case it'll be nicer to think of this as 2 pi over 8. Right? So at pi over 8 plus 2 pi over 8 gives me, this one is going to be 3 pi over 8. The guy in between this is going to be 4 pi over 8. I'm going to add 2 pi over 8 to this, so it's going to be 5 pi over 8. Add another 2 pi over 8, which means the guy in the middle here is going to be 7 pi over 8. Right? So I just want the middle points of each interval. So basically these are going to be the numbers I plug into my formula, and now I'm just going to plug and chug it. So actually no integration is involved here. So basically my midpoint rule approximation is going to be my delta x, which is pi over 4, times f evaluated at all these points. F of pi over 8 plus f of 3 pi over 8 plus f of 5 pi over 8 plus f of 7 pi over 8. And that's basically going to be it. So then we're going to go here, pi over 4. So f was actually the sine function, so I'm going to say sine of pi over 8 plus sine of 3 pi over 8 plus sine of 5 pi over 8 plus sine of 7 pi over 8. How would I find sine of pi over 8? If I have to find sine pi over 8, how would I do it?
Make the circle divide each and then.
Technically, yeah, but do you know the value of sine of pi over 8? How would you get to it?
Divide pi over 4, that's good.
You can think of this as, sure, pi over 4 divided by 2. And what does that remind you of? Sine x over 2? The half angle formula, right? We actually know what sine of x over 2 is. Right? Sine of x over 2 is equal to what? It's plus or minus the radical 1 minus cosine x over 2. So this is, I can take, I know it's going to be a positive radical because pi over 8 is in the first quadrant. So it's just going to be the radical of 1 minus cosine pi over 4 over 2. Plus this is going to be the radical of 1 minus cosine 3 pi over 4 over 2. Plus the radical of 1 minus cosine 5 pi over 4 over 2. Plus the radical of 1 minus cosine 7 pi over 4 over 2. Cosine of pi over 4 is radical 2 over 2. So this is 1 minus radical 2 over 2 over 2. What's cosine of 3 pi over 4? Because 3 pi over 4 is in the second quadrant, right? So my cosine gives me a negative value, so this negative becomes a plus. Radical 2 over 2. Plus 5 pi over 4? Because 5 pi over 4 is in the third quadrant, because you cut it up, and you know it's also negative, so again it's going to give you a plus. 7 pi over 4 is a positive value, so it's going to be minus radical 2 over 2. As far as I'm concerned, you can leave the answer here. That's basically it. So the important parts are, first you have to figure out the interval, which you just take from the limits on your integral, right? The lower limit is going to be the a, the upper limit is going to be your b. You're going to have to find the delta x, which is b minus a over n, which is going to tell you how you're going to want to break up your interval. If it's the midpoint rule, you want the middle point of each interval. And those you're basically going to plug into whatever function they put here. And you're going to add them all up, multiply by the delta x. Sometimes it can be nasty, like I've actually seen problems like this on a final. I probably wouldn't put a problem like this. I'd probably put a polynomial here or something like 1 over x to the 4th or x squared plus 1 or something like that. But I've seen things like this show up. Depends on who's assigned to write the final that year. So that would be how the midpoint rule would look. Any questions on that? So it's sort of tedious, but again, you never actually do any actual integration. It's just like plugging into a formula. This side. So let's look at how the trapezoid rule would look for this guy. So we're looking for T4. Again, here our AB is just 0 to pi, which means our delta x is pi minus 0 over 4, which is pi over 4. Which means since my interval goes from 0 to pi, I'm going to cut this into 4 pieces. This would be pi over 4, 2 pi over 4, 3 pi over 4. And so the trapezoid rule is just going to use these numbers, right? I don't have to find any averages. So the trapezoid rule is going to say T4 is equal to, I'm going to take that delta x and do what with it? Divide by 2. So I'm going to take pi over 4, divide that by 2. So I'm going to get pi over 8 on the outside. And then I'm going to have f of 0 plus what?
4.
2 f of pi over 4 plus 2 f of 2 pi over 4, which is just pi over 2, plus 2 f of 3 pi over 4, plus f of pi. So now I'm just applying that formula for the trapezoid rule, plugging in exactly the same numbers I see here. My 2 endpoints don't get anything, but everyone in the middle I have to multiply by a 2. So this would look like pi over 8 times f of 0 is just sine of 0, plus 2 times sine pi over 4, plus 2 times sine pi over 2, plus 2 times sine 3 pi over 4, plus sine of pi. So sine of 0 is 0. Sine of pi over 4 is radical 2 over 2. The 2's would cancel, so here I just get radical 2. Sine of pi over 2 is 1, so here I just get 2. Sine of 3 pi over 4 is also radical 2 over 2, because 3 pi over 4 is in the second quadrant, sine is positive there, so I get again a radical 2. Sine of pi is 0. So that's my whole thing. So I have pi over 8 plus times 2 plus 2 radical 2. Or I can even factor out a 2 and cancel it. So I would get pi over 4 times 1 plus radical 2 would be the approximation limit. So again, to run over the process, it's sort of straightforward, but it can be tedious, but it is straightforward. First, you figure out your intervals, which come from the integral. Lower limit is the a, upper limit is the b. Delta x you have to find, which is b minus a over n, always. Figure out what your interval looks like. You have to figure out where the numbers are coming from. Right? So you start with the 0 and the pi, you dissect it into how many times I tell you n, and you find out, you add the delta, start here and keep adding delta x to figure out all the numbers. Then you have to remember the particular rule you're using, what formula applies, right? So here it says take the delta x over 2 and then multiply by this sort of formula. Actually plug those numbers into the function that's given and compute them. Let's look at the Simpsons rule. Same function. We're going to repeat this process again to make sure we get it solid. C. So again, we're going to look at this, so we have to figure out our a, b. We look at the limits on our interval. A is at the bottom, b is at the top, so this is 0 and pi. Delta x would be b minus a over n, which is pi minus 0 over 4, which is pi over 4. So this means I go to my interval, 0 to pi. I'm going to divide it into 4 sections. So again, this is going to be pi over 4, 2 pi over 4, which is pi over 2, 3 pi over 4, and pi. And now I'm going to apply Simpson's rule. S4 is going to be equal to pi over 4 over 3, right, because the formula says delta x over 3, times, I'm going to use all these numbers. The first one I don't do anything with, plug into the function, but the second one I start off with a 4, so it's 4 times this, plus 2 times the second one, plus 4 times the last one, plus the last one. So this would be pi over 12. And again, now I'm just plugging these into my original function. So it's f of 0 is sine of 0, plus 4 times sine of pi over 4, plus 2 times sine of pi over 2, plus 4 times sine of 3 pi over 4, plus sine of pi. This is pi over 12. This is 0. Sine of pi over 4 is radical 2 over 2. I get 2 radical 2 here. Sine of pi over 2 is 1, so that just gives me 2. Sine of 3 pi over 4 is also radical 2 over 2, so I get 2 radical 2 here. Sine of pi is 0, so we have that. I can factor out a 2 here. This is just pi over 6 times radical 2 plus 1 plus radical 2. So I can just think of this as pi over 6 times 1 plus 2 radical 2.
What if your n was a odd number?
It will. You can't use this rule unless it's even. Okay. Simpson's rule is the only one that restricts you. You actually can't use it if you're given an odd number. The way it's set up, you need an even number of things to apply. That's the idea. Now let's look at the errors. So I just did a bunch of approximations, but what's the error for these guys? This is what we're going to want to know. This is taking forever. Want to be done with this by now. Okay, let's look at the errors. So this is actually problem 2 in our examples. We'll look at what are the errors. So for part A, let's look at the error with respect to the midpoint rule. This is b minus a cubed over 4 is 24 n squared. Like I said, after you pass Calc 2, you just forget about it. Like, you never use it ever again in your entire life. Okay, so the problem with this guy is the k we don't know. The main problem here in figuring out the error is figuring out the k. So let's look at that. The b we know, that's pi, a is 0, n is 4 in this case. The only guy we don't know is the k. Now remember, the k is just bounded by the second derivative. So I'm going to have to find the second derivative. So f of x equals sine x, which means f prime is cosine x, which means f double prime is minus sine x. So now I'm going to look at the function minus sine x. At this point, there are tons of ways to figure out when is it the biggest. But one way is you can actually graph it if you know, or if you know it's increasing, or so on and so forth. So minus sine x. What would it be here? Right. So in magnitude, the largest it is what? Is 1, right? So you know that sine x here is less than or equal to 1. So you could also do that. You know, the largest it could be is 1. Of course, we're taking things in absolute values because we're looking at magnitudes here, right? So in other words, I can just make k equals 1, and that will be good enough. So here, take k equals 1, since the second derivative of f is equal to just minus sine, which is bounded above by 1. So the error with respect to the midpoint rule is going to be 1 times pi minus 0 cubed over 24 times 4 squared. So basically it's pi cubed over 24 times 16, which is a relatively small number, right? That's the difference between the number I wrote for the midpoint rule and the actual answer is that number. So, I don't know if anyone has a calculator you can figure out. If you have a calculator, it would be fun to actually see how much that is.
The denominator would be 384. But
You're using your phone? That's going to take forever. Like on a test, you'd leave it like that. Of course, you wouldn't have a calculator, but I just thought it would be fun to see how far off it is.
So did you calculate it?
Yeah. Whatever that number is there. Let's look at the other ones. So the trapezoid rule. Here we remember that the error associated with the trapezoid rule is going to be k times b minus a cubed over 12n squared. Yep. Again, here you need to figure out the k because all the other guys are known so far. So then that's when you have f, you know, is sine. F double prime, you know, f prime is cosine. F double prime is minus sine. And since minus sine x is less than or equal to 1, choose k equals 1. If you had another function, you'd have to worry about some other things here. You'll come up with that situation in your homework, so you can try this. So here, the error associated with the trapezoid rule is less than or equal to 1 times b minus a cubed over pi minus 0 over 12 times 12 squared, which is pi cubed over 12 times 16. Which you will notice here that this is actually, is this smaller or larger than the last one? The denominator is smaller, therefore the fraction is larger. So this is a worse approximation in this case.
The first one was 1.28. This one is 2.54. If you want
1.28,
yeah.
and this is 2.54. Right. So if I compute the actual answer here and compare with the answer that we got from the trapezoid rule, the answer would be off by this much. So this is a worse approximation than the midpoint rule in this case. So get one more error, and then we'll do problem 3. Problem 4 you'll be able to do on your own. But problem 3 is a different kind of problem. I want to make sure you're not confused there. Let's do it all again for Simpson's rule. So we know that the error with Simpson's K times B minus A. This was actually the 5th power. Was that what I wrote the first time? I sort of remember writing a Q, but anyway. That's the 5th power here, and this is 180n to the 4th. Here though, your K should be less than or equal to the 4th derivative. So the size of your 4th derivative should be less than or equal to K. In this case, again, the 4th derivative is going to be easy to compute. F was sine, F prime is cosine, F double prime is minus sine, F triple prime is minus cosine, F to the 4th prime is positive sine, and since I know that sine is less than or equal to 1, just choose K equals 1. So here, the error according to Simpson. Right, the answer that I got for the Simpson, how far is it from the actual answer? Well, it's going to be 1 times pi minus 0 to the 5th power over 180 times 4 to the cube, 4 to the 4th. So this is just pi to the 5th over 180 times 4 to the 4th. What's that?
6.64. Wait, that's okay.
This is 4 to the 4th. It's actually 6.64. I feel like it should be smaller
Sorry,
than.
6.64 multiplied 10 to the power negative 3.
That's very different. 6.64 times.
10 to the power negative 3.
Was that supposed to be on some of the previous ones? Because that actually makes a big difference, right? So basically that's 0.00664, right? That's how far off we're from the actual answer. Right? So the difference between the actual answer and the approximation with Simpson's is this. This is actually the best approximation so far. Are you sure the first two you told me were right? 'Cause
Yeah, I think
they seem sort of big. Okay. In the third problem, it goes back to something I mentioned at the beginning when I said we can actually we can get as close to the answer as we want, right? The only thing that we change is the size of n. So basically, let's look at example 3, where I can say how many subintervals are needed. To approximate this integral, 1 up to 2 of 1 over x dx with an accuracy of 1/100th, right? Meaning 0.01, right? So let's say I want to do an approximation, but I want to approximate it within 0.01 of the actual answer. I can actually choose what tolerance I'm willing to accept, right? So if I only care about being accurate to the second decimal place, I can actually make it that way. The only difference is here, I have to figure out how many subintervals. What size n do I have to take in order to make this, approximate this, to that degree of accuracy? And all you have to do there is you're pretty much going to set up the error equation and set the error to be less than that number. And then you solve for the n that you will need to obtain it. right? So, did I say what rule I want to use? I said using the trapezoid rule, right? This chart sucks. Right? So I'm saying, if I use the trapezoid rule to approximate this, what should n be in order to get my answer within 0.01 of the actual answer? Right? So let's look at this guy. So we know the error associated with the trapezoid rule. That's going to be K B minus A cubed over what, 12n squared. Yeah, you write it down a couple times, you remember it, and then after you got Pascal 2, you forget it. Right, so now remember the only guy that we need to figure out here is we need to figure out n in this case, that's the important part. But k is still also unknown. Right? Remember k is bounded by the second derivative. Okay? So we're going to have to find the second derivative. F is equal to 1 over x. F prime is equal to negative 1 over x squared. F double prime would be equal to
2 over x.
2 over x.
Right. Now, what interval are we on? So we're on the interval 1 to 2, right? So on 1 to 2, 2 over x cubed is largest where? At x equals 1. Clearly here, as my x increases, the fraction decreases, right? So if I want the largest value, it must be towards the left endpoint, right? Because this is it's decreasing on 1 to 2. It's decreasing on 1 to 2. So obviously it's biggest when I'm over here, right? Sometimes it'll be obvious, sometimes you might have to do some other tests. But clearly x equals 1 is what we have here. Which means f double prime on this interval must be less than or equal to 2 over 1 cubed, right? So choose, in this case, I choose k equals 2, right? That will be an upper bound. So my error here with trapezoid is actually going to be 2 times b minus a, right? This is 2 minus 1 cubed over 12n squared, right? In other words, this is 2 over 12n squared, 1 over 6n squared, right? Now, so I know the error here in approximating this is this, but what do I want this to be? 0.01. So all I'm going to do is I set this to 0.01, right? This is what we want. Right? So this means I have 1 over 6n squared to be less than 0.01, which means 100 over 6 is less than or equal to n squared, right? Let's continue that over here. This means n must be larger than the square root of 100 over 6, right? Which is approximately what? This is 4.08. Right? So choose, how many subintervals would you choose to make sure we hit that target? 5 to be safe, right? So choose n equals 5 to be safe. Meaning, if I want to find the value of, so T5 would approximate this guy with 0.01 accuracy. So once I use 5 subintervals, I can get that to be within this much of the actual answer. Right? Less, right? Of course, I could have increased the tolerance here. I could put 0001. I want to be right up to 4 decimal places, in which case I just solve for that new value then. Right? This 100 could be 10,000, and I just make n big enough, right? The more I divide it into, the closer to the answer I get, right? So with the trapezoid rule, I'd actually only need 5 here. We'll stop there because this is getting tedious.
Is the homework due?
Ran out of time. Yeah, we've done enough for this section. So the homework for this is due on Thursday, and we will finish 6.6 on Thursday, which is actually going to be fun. It's not going to be like this. 6.6 is actually fun, and we'll see that. Add homework back for what.